There you go. I substituted the joke. All right, now, so when we look at these orbitals, these are going to be like addresses for electrons, okay? The easiest way to think of them is like little rooms for the electrons, all right? Or has anybody ever been on a train? That wasn't a lot of head nods. So we'll stick to the rooms. Oh, thank you very much for covering my door for me. Thank you. So when we look at these, when we're on a very small part, when we're really close to the atom, right, we're going to have very little space to fill in, okay? And so the easiest way to sort of think of these is when we look at these different periods, these are called energy levels, or they're called periods, right? And what they are is, this is your nucleus right there, and then you have, that was weird, the 1s orbital, which looks like a sphere, okay? And then you'd have the 2s orbital, which again looks like another sphere. Let's try this again. And it completely freaked out on me. Okay. All right, now, when we get out further from that nucleus, right, we have more space to fill in, don't we? Can everybody see it okay? There's just more space inside of this one than there is in that one, isn't there? Okay. And so that first one, that can only fit 2 electrons in it, okay, in that amount of space. In this larger space here, we can fit more stuff, right? It would be kind of like a pyramid. Your building looks like a pyramid, okay? If you're on the top floor, you can't fit a lot of stuff in it, can you? No. If you're a lower floor, you can now fit more rooms in it, can't you? Okay? And so we're going to be able to fit more rooms in here, and that's why, if you look at this periodic table, notice that we suddenly have 8 things that can fit in there, right? We suddenly have 8 electrons that can fit in there. And that's the 8 elements that's on that period. Everybody say it okay? Okay. Okay, remember that every time we add a new element, we're adding a proton, but we are also adding what? An electron, aren't we? Okay. So this periodic table has always been designed based upon the orbitals, the things you can fill electrons in with. Okay? Okay, and so this right here is the 1s orbital. In a single orbital, you can fit 2 electrons. That's the size of your room, okay? So you can fit 2 electrons in each of these orbitals or rooms. Now, when we get down to the 2, the second period, the second energy level, we have a 2s orbital right here, okay? And again, you can only fit 2 electrons in it. That's the size of the rooms, right? It's the size of the orbitals 2 electrons can fit in. If we come over here, these are now the p orbitals. Can everybody see that marker on those? Notice how they're a different coloring block? Okay. Okay, now p orbitals look like this. See those lobes? Looks a little like an infinity symbol or something. Okay. Now, when you look at that, notice that you have directionality to that now, don't you? When we were a sphere, it doesn't really have any direction, does it? Looks the same from every direction. And so there's only one sphere possible because it doesn't have any direction, right? Any other direction of looking at? The exact same space, isn't it? But if we look at p orbitals, they have directionality to them, don't they? So you could have 2 p orbitals without overlapping. Can everybody see that okay? Okay. And you could actually, in fact, have 3 of them, couldn't you? Where would the third one come? Is the real world 2-dimensional like my page? No, it'd come in and out, right? So one would be pointing out towards you, one would be going away from you, okay? And so that's actually what's happening here. There are 3 p orbitals. Each orbital can have 2 electrons in it, right? notice there are 6 elements right over here. Okay? That's literally filling in those p orbitals. That's why that looks like that. All right. Okay, so when we're looking at these electrons and we're trying to figure out where the electrons are, because for say we want to figure out what sort of light would be given off by this element. We want to figure out, is it going to be a semiconductor? We want to design a new semiconductor so we can make new computers. Okay? This theory is going to be what allows us to sort of do that theoretically. And so what we're going to do is we're literally going to make an address for each of these. Let's say we're doing hydrogen. That would be 1s, and then we would put a 1 as a superscript. The 1 in front of it is the energy level, period. Okay? How close it is to the nucleus. The s is the shape of that orbital. And then the 1 tells us we have 1 electron in it. Okay? For hydrogen, there's only 1 electron. So we're done. All right, so what if it was helium? Well, that would be, it's still on period 1, right? We just go over here, period 1, so we put 1. And then we put an S because it's still in the S block. Even though it's far right there, it's actually there, isn't it? Okay. Now, so that's 1s, and then how many electrons would be in there? How many electrons does helium have? 2. And so we're going to fill that room in, right? We're going to fill that floor in. And so it's going to get those 2 electrons in there. Okay. Now we go over here to lithium. Can we fit any more electrons in our S room? Our 1s room? No, we're full, aren't we? We're at capacity. So the teacher's going to go, nope, next classroom, right? Go. All right. And so that's going to be a 1s, 2 again, because we still have that room full. That's where 2 of those electrons are going to go. But we have a 3rd electron now, don't we? And so we're going to go 2s, and then there'll be 1 in there. You sort of starting to catch on to the pattern here? Eh? All right, we're just following along the periodic table and filling them in like they're rooms, okay? And so let's try beryllium, Be. So we would fill in the stuff before, right? Okay. And so that would be 1. And then what would we put? What's the only thing we can fill in up here? Okay, again, this is the S block. This is the P block. So the only thing that's available on this part is the S. So that would be 1s. And then there'd be 2 electrons in it. And then we have more electrons, because we're down here, right? Okay. Okay, and so we're again starting at the S block again, which is this first part here. So we're on the 2nd period, 2nd energy level. We would put a 2. And then again, it's the S block, right? So we would put an S. Now, how many electrons do we have? How many spaces are we into that? 2. And so that would be a 2 up here. Okay? All right, let's go one more. Boron. Okay? So again, if we're past something, then we filled all that in, right? So we can just fill that back in just like we did before. Because again, we're going to be the 1s2 and then 2s. I'm going to erase this real quick. Okay. Okay. So if we look at boron again, so remember, we're going to fill in to where we are on boron, right? Okay. So we're going to start up here, and we're going to go over, because that's what comes before, right? Okay, so it's going to be the first period, 1, and then the only orbital is this block here, which is the S block, right there. And so we're going to go S. And then we have 2 things that fill that in, don't we? And so that's going to be 2. Then we go to the next period, 2. Like going to the next floor, floor 2. And then we go, it's that first room here, we have to fill that in. And so it's S. And then we filled it in with 2 things, so it has to be 2. And then we're going to go, well, we're still on the second floor. So that's 2. But now we're in the green P block. Can everybody see the green P block right there? Okay. And that's P. That's what those orbitals are called. And we are only 1 space into that, aren't we? And so that's going to be 1, like so. Okay. Okay, so when we look at these orbitals, again, this is the periodic table is designed based upon the fact that we have to fill in these orbitals. Okay? It's literally a map of the orbitals. All right? Anything in this part right here, this green block here, those are going to be filling in p orbitals.
So if you were at like neon, would it be 2p10?
Oh, yeah. So this one here, remember you take 2 of the s's away here, right? Okay. So you're going to have 2 electrons that are used up filling in the s orbital here. So that would again be the same thing, 1s, 2 again. Then we'd have the 2s, 2 again. Then we'd be in the p's, right? And so that'd be 2p. And if we count over, 1, 2, 3, 4, 5, 6. So the B6. Yep. But you were close, you just didn't take off the previous. Yeah. Yeah. Okay. All right. Now try out carbon. Everybody ready for carbon? Okay. I'm going to clear my memory real quick, and I will mark carbon. What I want you to do is try to give me the electron configuration. Remember that you're literally just filling in the slots on the periodic table going down. You can help each other, talk to each other. Please do. Remember, in reality, it's not actually super complicated. It's, yeah, just like back away from chemistry is complicated for a second. Mm-hmm. You just do long thing. Yeah. Yeah. You can find people that put commas in, but that's wrong. Yeah. Fantastic. I'm hearing a lot of good stuff. Okay. All right, so what did we get for that? 1s2, fantastic. 2s2, fantastic again. 2p2, excellent. Perfect. Okay, That was exactly right. So let me ask you guys, have you ever heard of orbitals before?
Yes.
Yeah? Did they teach you that stupid pyramid thing? It has like the 1s and then 2. Yeah, yeah, all the s's are over here. Okay, so please just back away from that. Ignore that crap and just do it with the periodic table, okay? It actually is way easier. Out of the, oh, what is it up to now? 40-something students who have went, Dr. Clausen, I was taught this way and it works so great. I have asked them to try to actually do it and give me a correct answer. I have actually never seen someone use it and do actually get the right answer.
I think it's more so used for organization instead of configuration.
Yeah, I don't think that's. Like. Yeah, I think you're right that it's not really meant to do the configurations, but everybody tries to tell me that the configurations, I need that to do it. And that's, yeah. Now, honestly speaking, that pyramid thing is just completely nonsense and not necessary at all. Like, the periodic table is these orbitals. Like, that's why the shape's like that. You see how all the blocks stay together nicely? That's why the shape's like that. All right, there's a couple things I need to mention as we get down further in the periods. So as we get further and further away from the nucleus, right? What's going to happen? Well, we're going to get more space, aren't we? Okay? And that means we can fit more orbitals or more rooms in, right? And so when we get on this third period here, I know that only the 3s and the 3p's are filled here, but it actually generates 3D orbitals. There's space there. They're just really weird, awkward rooms. So what happens to weird, awkward rooms in your school? They get skipped, don't they? They only get filled when people have to fill them, right? Yeah. And the same thing happens here. These are very strange, slightly higher energy rooms, okay? Slightly higher energy orbitals. And so the 3D orbitals don't get filled until you're on the fourth period, because they're weird rooms, okay? Okay. And so that's why this is the 3D orbitals. Everybody see that? Yeah, they just get skipped for that first one. Now, when you look at the F orbitals, so keep in mind that these right here, these are actually embedded up in there, okay? So these F orbitals actually get made over here on the fourth period. There's enough room to create those F orbitals. But again, they're very, very weird orbitals, and they're very high energy in comparison, okay? They're just very awkward to fill in with electrons. And so they don't actually get used until all the way down here, right? That's how weirdly shaped and awkward they are, okay? They're like that closet that leaks over on the first floor or whatever. Is there a leaky closet room on the first floor? Okay. Yeah, probably not. Though the high school I went to was a brand new building that somebody had spent like $40 million to build, and they put it on top of clay in one of the rooms. The floor broke within the first year. Yep. So things can happen. Building actually got condemned in 7 years. Yeah. Yeah.
We have this kind of question on a test that we have in the table.
Yes, yes. I'm going to actually, what I'll do is I'm going to print off periodic tables. It won't have the nice S and D and P orientations on them, but all you need to understand is S, P.
Is it gonna be the full table or just gonna be that?
No, it'll be a full periodic table with masses, everything. Yeah, yeah, it'll actually be the full periodic table that's typically put into like a NIST. Yeah,
Can we use our own periodic table?
yeah, it's full notes. Yeah, go for it. Yeah, I'll just include a periodic table in case you forget. Yeah, full open notes, right? So feel free. Okay, let's try silicon real quick. Okay, so how would we do silicon? Is anybody starting to go, Dr. Clausen, I'm sick of putting this stuff on the previous periods? Anybody starting to get sick of rewriting those all the time? Okay, I'm going to teach you a quick way of doing that. Everybody ready for it? Okay, look at the noble gas before what you want to do. So in this case, we're doing silicon, right? And so the noble gas before that is neon, or Ne, right? So how you do this is you put a bracket, Ne, and then close your bracket. And now everything up to neon is accounted for. And I don't have to do those anymore. Okay? So go ahead and get me the rest of that for silicon. What's the next part? 3s, because we're on the third period, S. Are we filled in for the S's? We passed that? Yeah. Yeah, so that's 2. Okay, and then what's the next one? 3p, very good. And then how far are we into that one? 2. Very good. And that would be silicon. Okay. That saves you a lot of time, doesn't it?
So wait, you have to go to the nearest noble gas for that to work?
Yep. Yep. The previous noble gas, specifically, not just the nearest, okay? You don't. No, you can write them out long form. That's not a problem. Okay. It's just long. Okay, so how about sodium?
Like you have that for neon?
Na.
Can you just like start with neon on that too?
Yep, you can indeed. Yep. Bracket neon, that'd be fine. And then it would be what? 3s1, you got it. Yeah. Right. Nitrogen. Can you bracket neon now?
No, you can bracket helium.
You can. You can bracket helium. Yeah. Yeah. And then it would be perfect. 2s2, and then neon's right here. Yep, 2p3. You got it. Okay. And there we go in the atomic numbers. And the okay, so let's talk about some UV light here. So does everybody know of seasonal affective disorder, SAD? Yeah. Yeah, very common in places like the UK or up in like Seattle area. Yeah, because they have very, very cloudy weather. So this is going to be people who will experience mood swings and depression during winter. So some of the research suggests that SAD is actually a result of a decrease in serotonin or an increase in melatonin, and that's because when it's with fewer hours of sunlight. And so one of the treatments for SAD therapy is actually using what's called a bright light. It's essentially like a tanning bed light that's less extreme. Okay? And so you'd get a little bit of UV, and it will help you produce serotonin and decrease your melatonin. It's one of the light therapies that actually is proven to work, so kind of interesting. Okay. Anybody know where this energy comes from? Why it can produce UV light? How you choose to produce like a blue light versus a white light versus a yellow light? The wavelengths, and those match with the electron configurations. Yep. The electron configurations was how those things are decided. Okay, so one of the things that happens is the temperature with the seasons is a periodic property. We actually observe that in everyday life. Spring obviously is a little cooler than summer. Summer's a bit hotter than autumn. And winter is kind of the nadir or the low point of that temperature or cycle, right? Is everybody familiar with those seasons? Okay. Some places do not actually have 4 seasons. They only have 2 seasons, but you get the idea. We kind of have a winter and
I feel like autumn for 2 days.
yeah, we're abbreviated definitely. But yeah, we kind of. So, again, these are some of the electron configurations. This is just it represented in a slightly different way than I had just showed you. So some of the periodic properties are actually also follow along with this trend. And these are going to be things like atomic size, ionization energy, and metallic character. As we go down to the left, we're going to get larger sized atoms. As we go up and to the right, we typically get smaller sized atoms, okay? The big increases are going to be going up and down a periodic table. Kind of like when we go ahead and add a whole new floor to something, it gets real big suddenly, right? Okay. So, the ionization energy. Why can I stick a fork or like aluminum foil into a microwave and it sparks? And why doesn't it do that when I'm like microwaving my food? Anybody know? Mm-hmm.
Because the fork deflects some of the energy.
If it was just deflecting the energy, you'd actually get hit by microwave rays, and it wouldn't have sparks. Huh? You very much could, and there is actually, that's actually the satellite dishes. You guys have all seen satellite dishes. And then they have that little cone thing at the tip. What's happening is it's actually reflecting the microwave radiation into that cone so that the cone detector can detect more. Yeah. So interesting thing, you can actually take a microwave, if you could run it while it's open, trip this in, you could actually take a radio dish amplify it into a beam, and it will actually trash the microwave. Yeah. So anyways, now that we've talked about making a death beam. So ionization energy is actually the reason that happens. So when you're looking at metals, they're far down to the left, and they have low ionization energy. And so their electrons are not held very tightly. And that means that the radiation coming off the microwave is actually enough radiation to shoot electrons off of. Okay? And that's why you get the sparks coming off. It's literally that they have very low ionization energy. They ionize easily. They lose electrons easily. Okay? When you go up and to the right on the periodic table, this ionization energy is going to get very high. It's going to be very hard to shoot electrons off of these. Okay? How about metallic character? Which direction does that trend on the periodic table?
Decreases as you go right.
Mm-hmm. You got it. Less metallic as you go right. How about up and down?
It increases as you go down.
It increases as you go down. Exactly. That's why the metalloid line is diagonal, right? Okay. And so notice again, this is actually why it's called the periodic table, right? Because the properties are periodic and repeating as you go down the periods, aren't they? Okay. Okay, so the representative groups, 1A to 8A, the chemical properties are mostly due to the number of valence electrons. These are going to be the electrons that are in that outermost orbital. Okay? And so valence electrons, again, are going to be the outermost energy level. They're going to be the stuff on the surface or the outside. So they're going to be the stuff that's always going to get grabbed, or they're going to be the stuff that's always going to get interacted with. Okay? The group number actually gives you the number of valence electrons for those representative elements. That's actually why they do that 1A, 8A thing. It's so you can easily figure out the valence electrons. Okay. So this right here is a Lewis symbol. It's going to be a very convenient way to represent your valence electrons of an element. So the dots are going to be placed on the sides, top, bottom of the symbol of the element. So you can have a very easy way to look at valence electrons, and that's how many are on the outermost orbital, on the outside of the element. So the element aluminum actually has electron arrangements that are like a 2, 8, and 3. 2 being that 1s2. This being the second period, 8 electrons. This being the third period right here. It has 3 electrons. So what we do is we just take this outermost energy level, and that's the number of valence electrons. I don't suppose anybody knows what these other electrons are called. Yeah, they are not valence. That is absolutely true. If we're talking about the planet, everything on the surface is called the surface, right? Okay. The stuff in the middle is usually called what? The core. And so these are called the core electrons. Okay. And that's because they make up the core, and they're very difficult to get to, right? To get to them, you have to go through the valence electrons. Okay, so this is actually the Lewis symbol right here for aluminum. Is that fairly clear? Okay, clearer than mud? Fantastic. Okay. All right, so these are some of the Lewis symbols for magnesium. So again, it doesn't really matter where you place those electrons. You typically don't double them up until you have to double them up. Okay? So if you have 2 electrons, these are some of the different magnesiums. Again, it does not matter if you put them opposites, kitty corner to each other, whatever, okay? Just don't double them up until you have to. All right. So these are some of the different Lewis symbols for selected elements. Notice that some of these we start having to double them up. For example, that starts happening at nitrogen. See that doubled up right there? Okay, anybody ever heard of lone pairs? Yeah? Those are lone pairs. Okay, nitrogen has a lone pair. Right there, oxygen, that has 2 lone pairs. That's why you wait to double them up until you have to. Okay? Okay, so let's draw the Lewis symbol for each of the following elements. We have chlorine. What's that Lewis symbol going to look like? Again, there's a very fast way to do this, right? What group is chlorine? 7A. So how many dots do you have to put? 7. Exactly. You got it. Okay, and so we're going to have, what will that look like? In the middle it is? Cl. On the outside it has? 7 dots. And they're grouped into how many groups of 2? 3. Perfect. And then 1 is just off by itself. Yeah. Fantastic. Okay, selenium and potassium. If we look at selenium and potassium, they're going to look like this. Does anybody have any questions so far? No? Okay, fantastic. Let's talk about atomic size. This is again going to be determined by the distance of the valence electrons from the nucleus of the atom. So it's going to increase for the representative elements as we go from the top to the bottom of the periodic table. Those are going to be your biggest increases as you go and get more and more space added to it because you're lower and lower period. Okay? It will decrease going from left to right across a period. This is going to happen because you're going to add protons into the nucleus while not changing the overall distance, right? And so you're going to have these protons pulling those electrons tighter, okay? Going from left to right is a small difference, Just very small decreases. Okay? Going down a period is a huge difference, right? It's like adding floors to the house, right? Like big increases in the house's size, right? Okay, so this is what the atomic sizes look like. Can everybody see and appreciate those nicely? Fantastic. By the way, all of these trends are actually all related, aren't they? If you have more distance to your electrons, are they going to be as easy to hold on to? No, and so they're easier to pop off of it, right? And that's that ionization energy. Okay, so let's identify the larger atom in each pair. Will it be potassium or lithium? Potassium, you got it, and because it's lower on the periodic table, right? Lower period. Sulfur or silicon? Okay, so there's silicon, there's sulfur, right? Yeah. And so this is going to be going to the right of the periodic table. And so as we go to the right, it gets slightly smaller, right? Okay. And so silicon's going to be a little bit bigger. Okay. Potassium or bromine? Okay, so we look over here, potassium, and then we go over here, bromine, right? And so potassium's definitely a little bit bigger. Okay, fantastic. Let's identify the larger atom of the pair, which is just I hit the wrong thing. Ionization energy, this is going to be the energy required to remove one of the outermost electrons. It's literally the energy required to cause an electron to pop off of it. Okay? Or otherwise, in another terminology, make ions out of it, right? Because if you lose an electron, you become charged, don't you? Specifically, positively charged. Mind blowing. Okay, so this is the ionization energy changes. And again, notice it just directly correlates with the atomic size, doesn't it? Why is that? Same term, isn't it? If you hold on to it closer, it's easier to hold on to, isn't it? If you're barely holding on to it because it's way out there, easier to get it away from it, right? Okay, this is actually the photoelectric effect. It is one of Einstein's, this is sort of Einstein's first, what sort of made Einstein's career at the beginning is one of his first theories that was actually confirmed. Ooh, ah. Yeah, everybody told me you probably haven't done that, right? No. Anybody ever seen that before? Okay. So yeah, that's the photoelectric effect. What you're seeing is that metal there has a very low ionization energy as compared to like food or something, right? Carbon. And so when you microwave it, the energy from the microwaves is high enough that it can pop those electrons off of it. Electrons in motion is what we usually call electricity. Okay? Okay, so let's identify the element in each pair that has a higher ionization energy. Potassium or lithium? So potassium is lower on the periodic table, right? And that's going to mean it has a lower ionization energy. So you're getting the deals. So lithium is going to have a higher ionization energy typically, right? Yeah. Sulfur or silicon? Yeah, so sulfur is going to have the higher ionization energy. It's going to take more energy to pop those electrons off it, right? Okay, potassium or bromine? Bromine, yeah. So bromine's going to have the higher energy because it's going to be harder to pop those electrons off. So an element with element metallic character, again, is going to be one that loses valence electrons easily. Metallic character is going to be higher in the elements, metals, on the left side of the periodic table. It's going to be lower on the elements that are nonmetals on the right side of the periodic table, specifically top right nonmetals, bottom left metals, right? Same trend again. And so again, we have that overall trend of metallic character that matches the previous trends we've talked about. So potassium or lithium, which has more metallic character. Yeah, potassium. Which has more metallic character, sulfur or silicon? Silicon, exactly. Potassium or bromine? Yeah, this one's kind of nice because some of these are metals and some are not, right? Yeah. This is just a summary of that same relations. So given the following elements, let's answer the questions. Which is going to be the largest atom? Lithium, nitrogen, or fluorine? Yeah, you got it, lithium. Which is the highest ionization energy? Fluorine, exactly. Which belongs to group 5A? Nitrogen, yeah. There's kind of an easy way to do that, even if you don't know off the top of your head. And that's like the first one, right? And then this one's the one that's all the way to the other side. Okay, so which has the most metallic character? Lithium. Yeah, it's the only one that's even a metal, isn't it? Okay, and we have completed chapter 4. Woo! Yay. So, what time is it? Okay, I'm going to go ahead and let this time be reviewed. Does anybody have any questions? Anything you struggled with? Uh-huh.
It's not even that, but like, do you know that we have fall break October 6th, I think is the first day?
Yeah, I'm aware. Yeah.
I just,
No, thank you for reminding me, though. It is, like, I'll have that for anything else but this class, right? So, yeah, it's very possible I'll forget. If I do end up assigning something in fall break, just talk to me, okay? Yeah. You're exactly right. Super easy for me to forget, right? Okay. Hey?
Is it gonna be like multiple choice or like a mix of a bunch of
Multiple
questions?
choice. Yeah, yeah. It'll be a Scantron. Speaking of which, you'll want pencils, but I'll also bring some pencils.
how many, like, is it even for the chapters, like the amount of questions for each chapter, or is it like heavy on chapter?
It's as even as I can get it. Like, I do make mistakes, but yeah.
Does the review like the test, or does this have to be like math?
So the review actually has a randomized distribution of questions that happens for certain sections. And so it should be pretty similar to the exam, but it appears that I'm getting less math questions on some people's than I would have thought. Okay? If you want to see, you might want to try to take the review a couple times. And just if you're like, don't get any questions that you find interesting, you go, whatever. Okay? Okay. Yeah, and it will take your highest attempt. So. But I can't ask all math questions, right? Because math questions take longer. And so that would mean I can test you over very few things in the different sections, right? So.
Do you know what kind of questions that we'll be using, like equations? So we can review those more.
Every equation that I've covered has a chance of being there. Now, honestly, you don't actually need, really the only one that you would actually need an equation for is probably the Fahrenheit to Celsius conversion and the conversion factors for some of the imperials. Otherwise, you could just do unit canceling, right? But if you want to do a page with all the equations, that's fine. Oh yes, most definitely. Please bring a scientific calculator. You won't be able to use your phones, okay? Or really anything that does internet. Okay. Any other questions? Any questions on the material? No? Okay, what all does the exam include for chapters? Yep, 1, 2, 3, 4, all the way through 4. Okay. Fantastic. Dr. Clausen,
What would you say was the most missed on the last time you gave us?
okay, this isn't gonna help you, and it's so,
But never mind.
yeah. So the most missed questions the last time I gave exams are always stuff that's like too easy. So like, does chalk melt on a hot sidewalk? No, chalk doesn't melt on a hot sidewalk, but that was the most missed question on my last exam.
Oh, that's gonna be questions like that, isn't it?
Yeah, I'll do that. Like, they won't be all of them, but I will definitely do like, which of these things would melt, which of these things would, yeah. And I will do ones that are pure logic questions, and they are the most missed questions on all of my exams all the time.
So the homework is definitely more difficult.
Yeah, almost certainly.
Okay.
Yeah. Like you have unlimited, you have much more time to work on homework and open resources to do it, and you can get tutoring. So if I'm going to give hard questions, it's going to be on the homework, and then the exam questions always need to fit within that difficulty that you can actually do them in class. And if I give you like a homework question, some of those take like 10 minutes, right?
More than that.
Yeah. I mean, like you could get a 10-15 minute homework question. That's not really an issue. But a 10-15 minute exam question means I basically have spent a quarter of my exam time on a single question. And no, I can't test you over any of the other materials, right? Yeah.
Will there be questions like multiple choice?
Not typically, no. Now, there may be a block of questions which you have to refer to at the same table. Yeah. I do that every now and then, but mostly just because it's space saving to put one table instead of 5. Yeah. Any other questions? No? Okay. All right. I guess we can end early.